Hello, everyone. Today is the first talk of the day is going to be by Eliran Subag. So Eliran did his PhD advisement with Ofer Zaytouni and then went to do a postdoc at NYU, and now, if I understand correctly, is back at Weizmann. So just to remind you a little bit, if you have questions, then feel free to ask them in the chat. The organizer will try to help answer, and if necessary, we'll stop Eliran to ask him the questions, to transmit your questions. We'll have a short break halfway through, so that if you have further questions, to ask directly to Eliran. So I remind you all that this is recorded, so if you don't want your face on internet, please turn off your camera. At the end of the talk, which is going to be about 1 hour, we'll turn off the recording and the live YouTube transmission, and then you'll be able to ask your questions directly with your mic on. So with this technical stuff out of the way, I'll give it to Eliran to present his work.
Thank you. I need to share my screen, or?
Yes, please.
Yes.
Okay. Okay, thank you, Alex. Also thank you for the organizers for the invitation. I'll just start my timer so that Okay, so I'll start with the definition of the model. I'll actually show you two definitions. The first one is through characterization by a certain property. So what is a spherical spin-glass model? It's a sequence of Gaussian processes on the unit sphere, and the sequence is in the dimension. I'm using a bit of an unusual normalization. I'm taking the unit sphere. And the characterizing property of these models is that the covariance function, the covariance between the value at x and y, is given by n times a function, a mixture, a function which we call a mixture, sorry, applied to the inner product. This function does not depend on n. Okay, so this is what a certain consistency property which relates the models for different values of n. And of course, you might be interested on what functions nu are admissible. And so this is a question about positive definite functions on the sphere. And it is a classical question that has been answered by Schoenberg. And for nu to be admissible, we need to be able to write it as a polynomial in one variable with non-negative coefficients, and possibly this polynomial can be infinite. And the second definition, which is of course equivalent, is a realization of a process which has such covariance. So the claim is that if you take the process I just defined and you compute the covariance, you get what we had in the previous slide. So given a mixture, we take a linear combination with the same coefficients gamma p of the pure p-spin models, which I assume to be independent, and they are defined through the following formula. So x here is a point with on the sphere with coordinates xi, and you go over all monomials of degree p, multiply each one of them by a Gaussian variable, independent, and that's it. So essentially, this is the most natural way to define a random homogeneous polynomial. Now, I will mostly talk about two objects, the free energy and the Gibbs measure. And the free energy is a random variable that depends on the choice of a parameter beta called the inverse temperature. It's given by 1 over n log of the partition function, which is following integral over the sphere. And probably the most famous result in this business is the Parisi formula, which expresses the limit of the free energy as n goes to infinity to a minimum of some complicated functional, which I will not even write, applied to a measure, and we minimize over the space of probability measures on the interval from 0, 1. And this has been proved. It's a famous result by Talleyrand first, And later it was extended by Panchenko for the case of models on the cube with ±1 spins, and by Chen for the spherical models, which I'm talking about today. And both proofs were based on the ultrametricity property. Okay, and the Gibbs measure is a random probability measure on the sphere. So you simply take your random function, multiply by beta, and exponentiate. And use this new function, which is now positive, as a density on the sphere, and normalize everything so that the total mass is 1. And let me tell you about a nice property of this measure. So at an arbitrary point on the sphere, what we have is a Gaussian variable with variance of order n. So the fluctuations for most points on the sphere are just of order square root n. And the maximal height scales like n. And specifically, if you normalize it and take the limit, it converges to a certain number, which I denote by E star. This is so-called ground state energy, which of course depends on the model. Now, you can take an intermediate energy level between 0 and the ground state energy and look at the approximate level set. So by that I mean the set of points on the sphere where the energy is roughly this number up to some small error. What happens is that for any such energy value, you can choose beta such that the Gibbs measure is asymptotically supported on this approximate level set. Okay, so you have this family of measures, and you can put yourself at any height you want. And this is another way to study these level sets. But this is the way, this is the object physicists like to work with. So this is what we'll talk about. Now, the main result I want to tell you about is called the tap representation, and I'll start with classical tap representation. This is after Thouless-Anderson and Palmer. So what it says is that for any spherical model and any temperature, if you take Q to be the maximal point in the support of the Parisi measure, so if you remember, the Parisi formula expresses the free energy as a minimum over a space of measures. There's a unique minimizer, which is called the Parisi measure. And you take the support of this measure and take the rightmost point, that is Q. Then you can write the limiting free energy as the sum of 3 terms. The last 2 of them are explicit, given Q and your model nu and the choice of beta. And the first is the ground state energy, but computed over the sphere of radius square root Q, not the sphere that of radius 1 on which we originally defined the model. And just to comment, you extend your random function to the interior of the sphere, to the ball, using the same formula that we saw on the second slide. And this was originally, the tap approach was originally introduced in 1977 for the SK model, for the model with Ising spins. And Kurchan, Parisi, and Virasoro, and Crisanti and Somers derived this formula in the pure p-spin case for the spherical models. And there are many, many other works in physics about tap representations and other aspects of the tap approach, which I will not touch today. And mathematically, it has been proved in several cases. So for the spherical models, for the pure ones, you can prove this formula by looking at critical points and some analysis of what happens around them. So this was done for large enough beta, and later together with Benarus and Zaitouni for mixed models, but assuming they are close enough to pure. So essentially that one of the coefficients gamma p in the mixture is large and all of the others are small. Bellius and Kistler proved the formula for the 2-spin case, which is a unique case where the model is replica symmetric for all temperatures, so it's a bit different than the case P larger than 3. And Chen and Panchenko proved the formula, or an analog of the formula, which looks a bit different. It's slightly more complicated. for general models in the Ising case, so when you work with a hypercube. And this proof actually relies heavily on the Parisi formula. And today I'm going to show you a different proof in the spherical case. And the proof will be for a certain generalization, which I'll describe now. So I'm taking xi to be IID samples from the Gibbs measure. And I will call Q a value between 0 and 1, a good overlap, if for any fixed k and epsilon, I look at the probability that for the first k samples, each pair has inner product or overlap, which is roughly Q. And I want this probability not to decay exponentially fast. So we know of examples where if you take a value from the Parisi, the support of the Parisi measure, under some assumptions, we know that this probability will be lower bounded uniformly in n. So it will be essentially converge to a number. I'm allowing for Q to be a good overlap, I'm allowing this probability to go to 0, but not too fast, not exponentially fast. And an important remark, which I actually almost said, is that if Q is in the support of the Parisi measure, then Q is necessarily good. The other direction is not always true. For example, in the critical temperature, you can have Qs which are good, but not in the support. And here's the generalized top representation. So again, it holds for any spherical model and any temperature. And it holds for any Q which is good. Essentially, it's a characterization of the property of Q being good. And the formula now has the first two terms exactly as before, but the third term now is the free energy, the limit of the free energy associated to a new mixture. So nu Q is a mixture that you explicitly express using the original mixture nu and the value of Q. This is a function of T. So you start with your model and you choose a Q which is good, and then you get a new model. You need to compute its free energy, the corresponding ground state, and this is related to the original free energy using this formula. And why is it a generalization? Because specifically for Q, which is the maximal value in the support, what happens is that this model, this mixture, is what we call replica symmetric, meaning that the free energy is just half beta squared times the variance that corresponds to this model, which is exactly what we had in the classical representation. Okay, so this recovers the classical representation for Q, which is the rightmost point in the support. And before I move on, I want to mention that together with Weiko Chen and Dmitry Panchenko, we proved an analog of this representation in the Ising case for mixed models. It's more complicated, but I will not state it now. Okay, so now I want to move to talk about pure states. I'm doing it just to motivate some of the definitions and the type of questions I want to answer. I'm not going to use any information we know about pure states later in the talk, but I think it's a nice way to motivate the problem. So what is a pure state decomposition? First, it was proved by Talleyrand without relying on the ultrametricity property, and more recently, Jagannath gave a new proof which also generalizes Talleyrand's result using the ultrametricity property. What it says is that under some conditions, which are written in the footnote for specialists, you have a sequence of disjoint subsets of the sphere and the number Q star, such that the Gibbs measure of the union of those sets goes to 1. So if you're interested in the Gibbs measure, it's enough to understand what happens only on the pure states. And what's special about these sets, because this property by itself is not very special, so the important property of these sets is that if we take two independent samples from the Gibbs measure, X and Y, conditional on sampling from a pure state, their inner product or overlap is essentially Q star. So this holds for any epsilon. And also we have a sup over I. So it holds simultaneously for all pure states. Okay, so in some sense, it means that there is no further structure on the pure states if you're looking at the inner product. It's concentrated on one value. Okay, it's a degenerate random variable. Now, the following is actually a simple corollary from the theorem. So here I'm defining Mi to be the barycenter of the pure state, just the center of mass relative to the Gibbs measure. Now, you construct a new measure, G hat, which is, you just take your pure states and you shrink them to a point. Take the mass of a pure state and I put all this mass at Mi, and the rest of the mass, which will go to 0, I just throw to the origin. And then the distribution of the overlap under the Gibbs measure, the original measure, under this new measure, will be essentially the same. So in any reasonable metric, they will be close to each other with high probability as n goes to infinity. Okay, so in order to understand.
Someone asked if the probability in 2, how it behaves when n is large.
This probability? With high
yeah, I think so.
So let's say this is a random variable and it converges in probability to 0. Okay, the Gibbs measure itself is random. All of this is a random variable and it converges in probability to 0.
Yeah, I think
the question was about the rate of decay?
I think so.
I don't think we know anything about the rate of decay.
Thank you.
Okay, so what the corollary say, in some sense, is that you only need to know the location, the weights of the pure states and the location of the barycenter to understand the overlap distribution. Okay, so I hope I convinced you that this is an interesting object. And now I'm going to ask a sort of an imprecise question just to motivate what I'll try to do next. The question is, can we identify the barycenters of the pure state by quote unquote just looking at the random function? Okay, so I want a simple, nice condition, not something that goes through the Gibbs measure itself, but something that looks at the point at the value and maybe in a certain neighborhood of a point and be able to tell its pure state. But to understand really the pure state themselves, it's a very fine analysis. So, I'm allowing myself to look at pure state like subsets, which I didn't define, but these are subsets which have properties which are similar to pure state. Now, it doesn't make sense to ask questions about the subsets of the sphere themselves because essentially there are too many of them. So what I want to do is work with points in the ball inside the sphere, and I want to attach somehow a set which can be a candidate for a pure state. So going from a subset to a point, but by taking the barycenter is easy. It's obvious what we mean by that. But I want to attach to any point a subset in a natural way. It turns out that the natural way to do it is the following. So I'm defining a band around the point, which this is the formal definition, but let me use the picture. So the point is anywhere inside the sphere of radius 1, for example, this point. The band is constructed as follows. You take the orthogonal plane to this point in Rn, and you intersect it with the unit sphere. And then you give it some small width, which is this delta n. So delta n is some sequence that goes to 0 slowly, which we can fix now once and for all. And just to emphasize, the band is a subset of the sphere. It does not include the disk itself, so it's the boundary of this disk. Okay? Okay, so this is how I associate a set to each point, and I also want to associate free energy to M. And this is the same definition we used for the usual free energy, but now I'm integrating only over the band, not the sphere. Okay? And what you can check quite easily is that for pure states, conditional on sampling from the pure state, with high probability, the point will come from the corresponding band, from the band around the barycenter of the pure state. Okay, and for the pure states, we know that we have lower bounds on the mass of each pure state. We know that, I didn't state it before, but we know that the mass does not decay exponentially fast, and therefore the free energy, if I compute it only over one pure state, is roughly the whole free energy on the whole sphere. And because of this relation, I know that the difference between the free energy on the band and on the pure state will be small, because to get to the free energy, I need to take log of these quantities. So what we get is that if you take a pure state and you take its barycenter and compute this free energy on the band, then it's going to be almost the free energy if you were to compute it over the whole sphere. Okay, so there are points for which these bands are heavy, and specifically any barycenter is such a point. So now I want to change my question to, I want to look for points which has this property. Okay, so I want to work with bands and look for points such that the band around them is heavy, as heavy as it can be asymptotically if I compute the free energy. Now, if you think about it for a few minutes, you see that this condition is not so good because there are too many such points that satisfy this approximation. So actually, even if you understand what are the points, it's not going to be very meaningful and give you any good information. So what I want to do is look for points which are more special than this and require more. And the way the new requirement will come from, again, from pure states. So if you remember, and for a pure state, if we sample two samples, the overlap is concentrated on a single value. And that will happen also if you sample many points, let's say 10 points, and the overlap between any pair will be also this value, because just the degenerate random variable. And if you think of what it means in terms of this band, you get the following. So here I'm looking at the Gibbs probability. I'm taking k samples under the Gibbs measure, conditional on them coming from the band. And I look at the probability that xi minus ml dot xj minus ml for any pair is small. So what does it mean? If the 2 points are xi and xj are these two blue points in the picture, xi minus ml and xj minus ml are the two lines. And when epsilon is equal to 0, they are orthogonal in the sense of this picture. Okay, so here I'm looking at the probability that I take k samples, and they are almost orthogonal in this sense. Okay, I'm allowing some error, which is this epsilon. What happens is that for the barycenters of the pure state, this probability will be roughly 1. Now I want to define a new free energy, which is this old free energy, just the free energy on the band with that we saw before. And I want to add this term, log 1 over kn log of w. And this is a penalty term. It can only, because it's the log of some probability, it's going to be non-positive. So for some points, like the barycenters, it will be roughly 0. And for some other points, it will reduce the value. And so it will help me look at points which at a smaller set of points. This is just algebra, this equality. You can rewrite this definition as an integral with k replicas. So here you're integrating over k points from the band, and in the exponent, I have the sum of the values of the Hamiltonian at those points. But these are not, those points are not independent. There is the same restriction on the angles between the points. Okay, so that's just another way to write it, which looks more like a free energy than this term. And what happens for the barycenter, since this, before we take the log, this is 1, so after the log, this will go to 0. And for any finite k and epsilon, this will go to 0, and therefore for kn that goes slowly to 0, and epsilon n that goes slowly to, sorry, kn goes slowly to infinity, and epsilon n goes slowly to 0, you have the following approximation for at the barycenter. So this we saw before. Now I'm telling you that also this even smaller free energy will be roughly the total free energy. And this is the final question I want to ask. I want to find points, or to characterize the points which satisfy these two approximations. This is something I know that happens for the barycenters, and I want to understand if there's a simple condition or characterization for this to happen. So just to summarize, in the last few slides, the fact I used the pure set was only to motivate this definition. So I just want to summarize, I'm defining two free energies. The first one is just the free energy on the band with one replica. The other one is with many replicas, which are constrained to be roughly orthogonal. And we know that at barycenters, we have the two approximations here. And in general, we have these two inequalities, because the free energy on the band is definitely smaller than the free energy computed on the whole sphere. And because we represented this free energy as this one plus a penalty, which is non-positive, we have the other inequality. Okay. So the next thing I want to tell you about is a certain concentration property, which is really key to the proofs. And in order to state it, I need some notation. I'm going to define a centered version of those free energies by simply replacing h and x in the exponent by h and x minus h and m, the value at the center of the band. Okay, and if you define the centered free energy, and the same for the one with the replicas, you can just, you have the following two relations. You can just rewrite the free energy as the centered one plus the energy outside of the integral. So the logic behind this is that if you look at the process h and x minus h and m on the band and the random variable h and m, then they are approximately independent. So if I have something independent, I just want to pull it out of the integral and the log and have this formula. Now that we center the free energy, we have the following concentration result. You look at this replicated free energy, and you look at the deviation, its deviation from the expectation, and it converges to 0 uniformly over the ball of radius 1. Okay, and this uniform concentration is really important because we'll be interested in points essentially at random points. So, and actually this theorem is not very hard to prove. Mostly followed from a general concentration result for functionals of Gaussian variables, Lipschitz functionals of Gaussian variables. And the important thing is to set the definitions right. And after you get this definition, it's really easy to see that you have this concentration. So now, with this concentration result, I want to show you two immediate consequences. So the following sequence of qualities and inequalities holds for any point M in the ball. Okay, the first approximation is the concentration that we just saw. The equality is just from definition, and we already talked about two inequalities. This I have for any point. Now, what happens if Q is good? Actually, if and only if Q is good, with high probability, there exists a point M star on the sphere of radius square root Q, such that those two inequalities hold as approximate equality. So they hold up to an error term which goes to 0 as n goes to infinity. Okay, so what do you do with that? First, note that, so since for any m, so now I'm looking at points on this sphere, the sphere of radius square root Q, and for all those points, this expectation is the same, just by symmetry. It doesn't matter which point I'm choosing on this sphere when I'm computing the free energy, because it's expectation, it's not, it's going to be symmetric. And I know that for any m on this sphere, this quantity is smaller than the free energy. And therefore, if I have a point where it achieves the free energy, then the energy must be maximal at this point. Okay? This is really simple. Since it's always a lower bound for this, and I have an equality, it must be maximal. And then, just by looking at this point with this property, so on the left-hand side, I'll have E star instead of this energy. And I know that for this point M star, these are approximate equalities. And therefore, just by comparing the two sides, you have that the free energy, if Q is good, the free energy is asymptotically the beta times the ground state energy at radius square root Q plus, so you need to take limits. So if you take the limit in n, what we'll have is the limit of this free energy. This is almost the top formula. Okay, so if you remember the top formula, we had this term, we had two terms instead of this one, which I'll talk about in two slides. But if you follow it, it's really just a few arguments and you already get the top formula. There's another immediate consequence. Now that I know that this is the free energy, I can just substitute it in the right-hand side. And therefore, for any on the sphere of radius square root Q, I have a characterization for the points that we were interested in, the points where those free energies are approximately the same, because, okay, what you'll have here is just beta times E star and this expectation, which you also have on the left-hand side. So for these two inequalities to be approximately equalities, we must have that this energy is E star, which will appear on this side of the formula. Okay, so in words, if I look at points on the sphere of radius square root Q, and I want to know which are the points such that the band has the free energy, which is roughly the total free energy, and such that the measure is spread on the band in a way that allows me to sample many points which are orthogonal on the band with probability which is not exponentially small, then the answer is that these are exactly the points which approximately maximize the Hamiltonian. Okay, so you can just look at the value of the Hamiltonian and decide if the band has this property or not. Now, let me go back to...
I'm asking if the pure state decomposition theorem depends on beta, the temperature.
Well, what it holds for any beta, but for example, if you're in the high temperature phase, what you have is one pure state, etc. So there are things which I didn't mention, like the weights of those pure states, which will depend on the model, will depend on beta. I will talk later about the ultrametric tree. The structure of the tree will depend on beta, but the fact that the theorem is true does not depend on beta. I mean, the way I stated it, it can be degenerate in a sense if you're below the critical beta. We'll have just one state at the center.
Thanks.
You're welcome. More questions or? Okay.
No, it's good. I asked in the chat if anyone had any. So
okay, thanks. So now I want to go back to the Tapper presentation. And so what is missing is in the presentation is just to prove this equation. This is what I showed you in the previous slide, and this is what we have in the Tapper presentation in the beginning of the talk. And I will not explain how to prove it, but I just want to show you where these two terms come from. So the first one is quite easy to understand. If you take the band, so we're working with points on the sphere of radius squared q, take an arbitrary such point and look at 1/n log of the volume of the band and take the limit. This is what you get, this logarithmic term. So this is just an entropy term. And the second term arises as follows. So take one such point, and now think of this is a very thin band. We took its width to go to 0 as n goes to infinity. And I want to think about it as a sphere of one dimension less. Okay, so it hardly varies on this axis. So I would think of it as a sphere. And I want to look at this process with which we define the free energies, h and x minus the value at the center, as a new spherical model on this sphere. Okay, it will be a process whose covariance only depends on the angle of 2 points. So it will correspond to a spherical model. And you can compute the covariance, the dependence of the covariance on this angle. And this is how I'll define the coefficients alpha p. So you do some computation, it takes half a page, and you see what you get for this coefficient. It will be the mixture will be a polynomial, and you can compute explicitly this alpha p. And then what I want to take is not exactly this mixture, but I want to remove the one spin interaction. And this new mixture is the mixture whose free energy is what appears in the top representation. Okay, so I just wanted to show you the relation to how this free energy is connected to the Hamiltonian on the band. Okay, so now I want to go back to talk about the pure states and the ultrametric tree. I'll explain what that means. So let me just remind you, this is how we motivated the definition of the free energies. We know that at barycenters, all free energies are approximately the same. And it's not difficult to verify, it's pretty immediate, that asymptotically, the barycenters, if you look at the norm squared, it will be Q star, which is defined as the maximal point in the support of the Parisi measure. So from the characterization of such points, we know that now that the energy at the barycenters is the maximal energy on the sphere of radius square root of Q star. Okay, so that's an immediate consequence about the energy at the barycenters. And now I want to talk about the ultrametric tree. So first, let me start with the Parisi ultrametricity answer. That's one of the most famous and important results in spin glasses. It was proved by Panchenko. And so here I'm taking epsilon constant n to infinity, and x, y, and z are 3 independent samples from the Gibbs measure. And what the property says is that the overlap of the first pair is at least the minimum of the overlaps of the two other pairs minus some error, which can be as small as you wish. So if you fix epsilon and then take n to infinity, epsilon can be as small as you wish. And this happens with probability that goes to 1. And the way I want you to think about it is as a transitivity of the following relation. So you can define a relation on the point. So you think that we take many samples from the Gibbs measure, and then we define the following relation. If the 2 points are in the relation, if the inner product is larger than Q, then this essentially means, not exactly, up to small errors, it means that this relation is transitive. And so it's actually an equivalence relation because the other properties are immediate. And the equivalence clusters are nested in the sense that if you increase Q, if you look at Q prime larger than Q, then what happens is that you just break down the equivalence classes into smaller classes. So, okay, so you can think of Q equals 0. You have all the samples. Let's assume that the overlap distribution is positive always. So at 0, you have all the samples, and then you increase Q, and you form these equivalence classes, and you break them down as you increase Q, and you have this hierarchical structure of clusters. And you can also talk about this hierarchy in terms of subsets of the sphere, not just samples. And so this was done by Jagannath in the theorem. Actually, it's the same work I mentioned before, where he constructed pure states. So I just want to explain what the theorem means for the pure states. I don't want to, I just want to express it in the way that is relevant to what I want to explain. So what he showed is that if we look at the pure states, or that's equivalent to one of his results, you can arrange, so you can arrange the barycenters of the pure states in a tree structure such that the leaves are going to be the barycenters. And it has the following geometric property: any two edges are orthogonal to each other. These are not necessarily edges which have a common vertex. Simply any two edges on this tree are orthogonal to each other. Okay, and now maybe partly answering one of the questions that was answered before. What changes between model and different temperatures is qualitatively what changes, because there are other things that change, but the number of levels of this tree depends on the size of the support of the Parisi measure. And when the support is finite, this is what we call finite replica symmetry breaking or finite step replica symmetry breaking. When the number of atoms is k plus 1, we say that the model is k-RSB. And for example, in this picture, this corresponds to 3-RSB when the tree has 3 levels. And in a moment, I want to talk about full-RSB models for which the support is an interval from 0 to Q. And in this case, what happens is that the number of levels to this tree goes to infinity, as n goes to infinity. And the radii, so if you look at all the vertices and the radii, then asymptotically, they will cover this whole range. Okay, so you should imagine something which is this huge tree that in the limit is going to be almost a continuous structure from the origin to the pure states. Okay, now how is this relevant to what we talked about before? Let's take a point. For example, in the picture, I'll look at this green point. So this is not the center of a pure state. It's an internal point of the tree, not the leaf. And I want to look at the corresponding band. So from the orthogonality property, all those edges are orthogonal to this vector, which is the location of the green point. So these are all the descendants are going to be points in this disk, which is the orthogonal hyperplane. And what happens is that the intersection between this band and the bands which corresponds to the pure state is such that there is enough mass on this band, this large band. And in particular, the free energy of this band will be roughly the free energy of a pure state, which is roughly the free energy of the whole sphere. And also, since the centers of the pure states are orthogonal relative to this point on the band, what we'll have is that this other free energy, which was related to the ability to sample orthogonal points, will also be roughly the free energy without replicas. So what we conclude from this is that the energy at any point on the sphere is maximal compared to the same sphere, to the sphere of the same radius. Okay, so this holds uniformly over the tree. Any point has the maximal energy. Now I want to go back to this picture and recall that in this tree, any two edges are orthogonal. Now we know also that the energy is maximal at any point. And I want to talk about the full RSB case, where this tree is really dense in some cells. And I want to relate this to the problem of optimization, because now suppose that we take beta to infinity slowly. So what will happen is that the centers of the pure state will be very close to radius 1. And we have this huge tree, which we can hope to somehow follow from the origin to get to one of the points and get a point with maximal energy. So let me be more precise. And here's a problem I'm interested in. So you're given the Hamiltonian, and what you want to do is find a ground state configuration, a point on the sphere where the energy is roughly maximal. And precisely what you get as an input are the coefficients that define the Hamiltonian, or the JIs. And you want to design an algorithm that produces such point with minimal time complexity. Okay, so here is the result. So what you need to assume is this full RSB condition that I mentioned before. I want to assume that for any beta, the support of the Parisi measure is an interval from 0 to q. For small beta, this will be a degenerate interval. It will be just a point 0. But for large beta, it will be an interval. And then the theorem says that there is an algorithm which produces such a point up to an error of epsilon, and its time complexity is n to the degree of the mixture. Okay, so what is this n to the degree of the mixture? It's just, if you think about it, the number. So let's assume that the mixture is finite. Otherwise, the way I stated the problem doesn't make sense. If the mixture is finite, the number of coefficients you have is of this order. Okay, so that's the minimal complexity you can have, just storing the coefficients. It turns out that with this complexity, you can get to an approximate ground state energy. And of course, in the end, by diagonalizing, you can get an error epsilon n that goes to 0 if you allow anything that is asymptotically larger than n to the degree of nu. I also want to comment that for the spherical models, this condition is equivalent to the following explicit condition. You just need to check whether nu double prime to the -half is a concave function on the interval 0, 1. Okay, so you can just replace this condition star by this one. And the last comment about this theorem is that it was recently proved by Montanari and then by El-Alawi, Montanari, and Selke, and I think Andrea will talk about this in his talks. A similar result in the case of Ising spins. So when you optimize over the hypercube instead of the hypersphere, and what they do is they use a certain class of message passing algorithms, and they show that under a similar condition, you have the optimal such algorithm will get you to the ground state energy. Okay, so now on to
we had a couple
question.
If you want just to make sure. So
sure.
One person was asking if this theorem here, the beta was arbitrary. So,
this theorem?
Yeah.
So it's a theorem about, okay, maybe I should have said that the words with high probability are missing, but okay, so the theorem means that there's an algorithm that with high probability, given the random function Hn, which comes from a model, from a mixture which satisfies this property, with high probability, the algorithm will produce such a point.
And then the other question was if the algo is explicit.
Yes, I'll show you in a second what is the algorithm explicit.
Thank you.
Okay, so before I show the algorithm, I want to tell you how you obtain this algorithm, what's the idea. So I'm going to assume this condition, and technically I'm going to take beta to infinity with them. Don't worry about this. And what I want to do is look at only one path from the tree. So it's a discrete, the tree is discrete, so I'm going to interpolate this path linearly between the points, and I will parameterize this path so that at time q, the point is at radius square root q. Now I'm just going to tell you about two properties inherited from the tree. So the first one is this orthogonality property. And specifically what I want to note is that each of those segments is orthogonal to the current position, because the current position is the sum of all the previous segments, and all those segments are orthogonal. So in particular, any segment is orthogonal to the current position. The second property is what we saw on the tree also holds on a path on the tree, from the tree. The energy is maximal at any point. So essentially it's maximal at any of the points on the tree itself, but since assuming this condition, I will have infinitely many vertices on this path as n goes to infinity. So even between the vertices, it would be roughly maximal. Okay, so now I know that I have these two properties for any path on the tree. And all I want to take from this is the knowledge that such paths exist. I don't want to use it in the proof. I just want to think how we can construct such a path by ourselves if we didn't, because we can't just pick a point from the tree. Of course, we know it exists, we know what the properties are, but we can't just say, let's take a point from the tree. So now let's think of how we can construct a path with these two properties by ourselves. So the first property we can just impose. I just want to build a path by concatenating many directions which are orthogonal to the current position. So just summing over the previous steps, normalized correctly. So after k steps, I will be at radius 1. And every time I choose a new direction, it has to be orthogonal to my current position. But of course, you want to choose those directions to be able to say something about the energy. Specifically, we want to maximize the energy locally at each step. And maybe the first guess should be to use the gradient, because that's what we want to do, go in the best direction in terms of the energy. But this is a bad idea, because if everything goes well, we should have at time I, we should have a point which has the maximal energy on the corresponding sphere. The gradient should be approximately 0. And what I want to do is simply take the second order approximation. So choose a direction in the span of eigenvectors that correspond to the largest eigenvalues of the Hessian computed on the orthogonal space to your current position. This actually works. So precisely, the algorithm goes as follows. Pick some large number of steps k, some small error delta, initialize arbitrarily for the first step, it doesn't matter, take some point with radius 1 over square root k, and then at each iteration, choose a direction, a vector of length 1, which is orthogonal to your current position. I also want to require that the projection onto the gradient is positive. I'll show you why in a second, essentially to avoid dealing with the first order term in a Taylor expansion. And note that if it's negative, I can just flip the sign and have the other inequality. And the important property is that the second order approximation or the second order derivative in the direction of v is almost the maximal you can get up to this error delta. And then I simply update by taking a small step in this direction. Okay, and I continue this way until after k steps, I end up on the sphere of radius 1. What you can show is that the energy on the path is consistently maximal up to this error epsilon. And you can make epsilon to be as small as you wish, provided that k is large enough and delta is small enough. Okay, so this simple algorithm gives you a path which is consistently maximal. And as for time complexity, you can check that one iteration takes some constant times L to the degree of nu, and you need to run k iterations. So you have a constant that depends on delta and k, and therefore depends on epsilon. And lastly, this is the last slide. I'll explain in a minute how you prove the correctness of this algorithm. So you want to control the energy on this path. So you need to control the Hessian, because that's how you choose the direction, at any point on the path. But you can actually control it uniformly in the ball. What you can prove is, in an appropriate sense, that for any point in the ball, the edge of the spectrum of the Hessian computed on the orthogonal space is roughly 2 times nu double prime q to the power of half, and q and x are related by this condition. Okay, so the radius of q is square root, the radius of x is square root q. And now you just Taylor expand, and you see what you gain from one step. So this is where we started. If you recall, I wanted the projection onto the gradient to be positive, so I can conveniently forget about the first order term here and just put the second order term, which I control using this proposition. You have some error which behaves, it's a different power of k. And then if you want to control the energy, essentially by concatenating these increments, what you get is an approximation of the integral of this function. So now we have this lower bound on the energy. And by some other argument, for example, by the Parisi formula, under the condition star that we assume in the theorem about optimization, we know that the ground state energy at radius square root q is exactly this integral. Okay, so you prove that your path achieves this energy, and you know by some other argument that this is the maximal energy, and therefore you finish the proof. And I'll stop here. Thank you.
You should all have the ability to unmute yourselves now. And so I suggest we give a lot of applause to Eliran for a very nice talk.